for. Right? For our second and third laws, one is the system, and that's the reaction we're looking at, and the surroundings, that is everything else. Both undergo changes in entropy during physical and chemical processes. The entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. An equilibrium process is one that's caused to occur by adding or removing energy from a system that is in equilibrium. So our second law of thermodynamics, in any spontaneous process, there is always an increase in the entropy of the universe. The local entropy may decrease, though. So you are ordering your room, right? You're putting things away in your room. You're stacking those oranges, because for some reason you got a bunch of oranges in your room, into a nice, neat stack. You're fighting entropy, right? You're decreasing the entropy of those oranges. But it comes at a cost. It comes at a cost of you providing the energy to do that. You are consuming food. You are metabolizing it. And the overall universal, the surroundings, everything else is going to gain entropy. All right, so you are sacrificing universal entropy to increase the order locally. That's how things look like they're self-organizing, right? How does life evolve? How do things seem to spontaneously order themselves like a crystal when it gets cold, right? Well, it's because you're trading local entropy decreases for global entropy increases. The entropy of the universe is increasing always, but the total energy of the universe is constant because of the first law of thermodynamics. And the change in entropy of the universe can be represented by changing entropy of the universe is going to be that of the system and the surroundings. So what happens to the system? Those are the changes that occur in the system, and what are the entropy changes in the surroundings? If the entropy of the universe is positive, and the entropy of the universe increases, then the process is spontaneous in the direction that is written, right? Because we can have both a spontaneous and a non-spontaneous reaction. We generally tend to call that spontaneous reaction by another name. That's usually the forward reaction, right? That's the one where K is big. K is greater than 1. Right? We've got a big K. If the delta S of the universe is negative, then the process is spontaneous in the opposite direction, or the reverse reaction, and that's where K is less than 1. If the entropy of the universe is 0, the process has no tendency to occur, right? And that's when Q is equal to K. So our body spends a lot of energy to keep its system out of equilibrium. So if you reach thermal equilibrium with a room at 20 degrees C, that's bad, right? You don't want your body temperature to be 20 degrees C. Right? If your internal body temperature was 70 degrees, you're having a bad day and you're probably a corpse. Right? So in our second law, in a living cell, large molecules are assembled from simple ones. Is this process consistent with the second law of thermodynamics? And the answer is yes, it is. We're not escaping these thermodynamic laws, no matter what we do. So our solution to reconcile the operation of an order-producing cell with the second law of thermodynamics, we must remember that delta S of the universe, not the system, must be positive for processes to be spontaneous. A process for which delta S of the system is negative can be spontaneous if the associated change in the surroundings is both larger and positive, right? And the operation of a cell is just such a process. Right. What about the effect of temperature on spontaneity? So delta S, our entropy of the surroundings, is going to be determined by heat flow. So exothermicity is an important driving force for spontaneity. So heat does matter. So exothermic processes increase the entropy of the surroundings, right? Because now my outside world, my universe, has picked up more energy. My molecules are moving faster. They've got more places they can be. Right? The energy flow increases the random motion of the surroundings. The significance depends on the temperature at which the process occurs. So some processes are going to be temperature dependent. They'll be spontaneous at one temperature and not spontaneous at another temperature, like ice melting, right? So ice melting is a very good temperature dependent process. It's going to be spontaneous above 0 degrees Celsius. It'll be non-spontaneous below 0 degrees Celsius. The impact of the transfer of a given quantity of energy as heat to or from the surroundings will be greater at lower temperatures. Right? So if you're running it cold, that little bit of change in heat is going to be a big relative difference. So when you've got an exothermic reaction, heat is going from the system into the surroundings, and our entropy goes up. When an endothermic reaction happens, right, heat's getting transferred from our surroundings in our endothermic reaction, our entropy is going to go up, right? Our entropy is going to go up inside the beaker, but the entropy outside, that's my surroundings, is going to decrease, right? Because I've moved my heat from one to the other. The sign of delta S on the surroundings depends on the direction of the heat flow. Delta S surroundings is positive for an exothermic process, and delta S of the surroundings is negative for an endothermic process. The magnitude of delta S on the surroundings depends on the temperature. Now, so remember that equation way back when we saw with Herr Boltzmann, and we're like, okay, well, we've got like K and Ln and W, right? And you're looking at things with some temperatures, right? So it's going to be temperature dependent. Right? The tendency of the system to lower its energy becomes a more important driving force at lower temperatures. Right? So the driving force provided by the energy flow, or heat, is going to be equal to the magnitude of the entropy changes of the surroundings. So we're going to say the quantity of heat divided by the temperature. And for an exothermic process, that entropy change in the surroundings is going to be positive, quantity of the heat divided by the temperature. And for an endothermic process, it will be negative, quantity of the heat divided by the temperature. So we got this nice little reaction or equation that we can develop that says at a constant pressure and constant heat flow, where the heat flow is the change in enthalpy, delta H, we can relate delta S and delta H to each other. So we've got S, H, and T, and you can come up with your own ways to memorize the SHT equation. So SH minus negative sign in there, and it's going to be over the temperature. Right? So we can look at our interplay between our system and our surroundings entropy to figure out whether this reaction is going to be, a given reaction will be spontaneous. If my systems change is an increase in entropy and my surroundings go up in entropy, my delta S of the universe has to go up, it will be spontaneous. If I lose entropy in my system and I lose entropy in my surroundings, the entropy change of the universe will be negative, and we cannot have that. The reaction will not happen. It's got to go in the opposite direction. Okay? When we mix and match, so if my system's entropy goes up, but my surroundings entropy goes down, we don't know about the enthalpy change or entropy change of the universe. It will be spontaneous if the entropy change of the system has a larger magnitude than that of the surroundings, right? So it's going to be positive if my system is bigger than my surroundings. Right? I take like 10 and I got minus 5, I'm going to end up with plus 5, right? That would be spontaneous. If I've got 5 and I'm going to do minus 10 and I add those together, I'll have minus 5, it won't be spontaneous. Right? If we flip those around and I've got a negative change in my system and a positive change in my surroundings, again, we do not know. It's going to depend on which one is bigger. So it will be spontaneous if delta S of the universe is positive, which means that my surroundings has to be larger in magnitude than my system. So let's look at another example. So in metallurgy of antimony, the pure metal is recovered via different reactions depending on the composition of the ore. For example, iron can be used to reduce antimony in sulfide ores. So we're going to take Sb2O3. We're going to react it with some iron, and we're going to get 2 Sbs and 3 FeSs, and it's got a delta H of negative 125 kilojoules. And carbon is sometimes used as a reducing agent for these oxide ores. So we've got Sb4O6 reacting with 6 carbons to give you 4 Sbs and 6 CO2s. And here our delta H is positive. Can we calculate the delta S of the surroundings for each of those two reactions at 25 degrees C and 1 atmosphere? No, we already can guess something about the surroundings. Like we can guess about the sign on the surroundings, because if this is a spontaneous process and we got a negative over here, we know that we're going to have a pretty large increase in our surroundings. Here this guy is positive. Our change in the entropy of the surroundings could be positive or negative. We don't know on the magnitude yet. All right? So we're going to use our formula that says we're going to calculate delta S as being related to delta H over T, where T is going to be 25 plus 273, 298K. So for our surroundings, for our sulfide ore, we're going to take that minus 285 kilojoules per mole divided by 298 Kelvin, and we're going to end up with 498 joules per Kelvin. And it's going to be a positive number. Note that the delta S surrounding is positive, as it should be, since the reaction is exothermic and heat flow occurs towards the surroundings, so you're kind of getting the idea that entropy is going to go up just based on the heat, increasing the randomness of the surroundings. For the oxide ore reaction, our entropy of the surroundings is going to be minus 778, because this guy was a positive, divided by 298. So we get minus 261 kilojoules per Kelvin, and we get minus 261.61 times 10 to the third joules per Kelvin. So in this case, the entropy of the surrounding is negative because the heat flow occurs from the surroundings to the system. All right. And this brings us to one of the most important concepts, and that is delta G. So some people love to talk about how free energy can be used to justify perpetual motion, right? It's energy and it's free and we're just tapping into that, or faster than light travel, or all the kinds of crap. In reality, free energy is just the ability of a system to be able to do work. It is free in the sense that it is not currently occupied, right? Yeah, I'm free on Saturday to come into work, that kind of free, not like, oh, you're going to come in and I'm not going to pay you kind of free. So that kind of work is exactly what such scammers are trying to avoid. Right? So delta G and the work a system can do. For a spontaneous process, delta G is the maximum work obtainable from the system as the process takes place. So delta G is going to be related to the maximum amount of work. For a non-spontaneous process, delta G is the maximum work that must be done to the system as the process takes place. So can we kind of throw energy into something and make a non-spontaneous reaction happen? Yeah, we do it all the time, right? That's what our bodies are doing when they're keeping us out of thermal equilibrium. That's what we're going to do when we do electrolysis of water to generate hydrogen. There's lots of things that are going to, or electroplate of metal, right? There's lots of things that are non-spontaneous processes that we will drive by giving them energy. Of course, the energy of the universe still always goes up because that energy had to come from somewhere. Right, so delta G is equal to our maximum amount of work. So if I've got a little gas cylinder right here that's hooked up to a little weight and piston, right? As the expanding gas can do work by lifting that weight, right? So as your gas expands, it's got a new position on the piston. It moved that weight up, right? So it went up in gravitational potential energy. It's done some work. And this is called Gibbs free energy. That's why it's got the symbol G. The thermodynamic standard state, the most stable form of a substance at 1 atmosphere pressure at a specified temperature, usually 25 degrees C, and 1 molar concentrations in solution, is going to give us our G naught, or free energy of that particular molecule. So the Gibbs free energy, expressed in terms of enthalpy and entropy, refers only to the system, but it can be used to predict spontaneity. And so that's how you're really going to do this spontaneity reaction stuff, is like you're going to look at delta G, right? Because it's going to be this combination of both heat and entropy that are driving our system at a particular temperature T, right? And so if delta G is negative, if delta G is positive, or if delta G is 0, those are going to be the criterion for spontaneity. All right, so let's take a second. We'll talk about Josiah Willard Gibbs, so famous American scientist back from the days when scientists had beards and were all European. America was kind of a backwater at the time. We were not up on everybody's smart list. It was all Germany and France, and they were the real movers and shakers in terms of the natural scientists at the time. And he was one of the guys that actually managed to garner respect by just going hardcore on some of this chemical physics stuff. So him and Lewis are really some of the bright shining stars in early American chemistry. His work was deemed as one of the greatest scientific achievements of the 19th century and one of the foundations of physical chemistry, which is its own whole branch of chemistry. You got organic and analytical and inorganic, and physical chemistry is one of those. So some of the important things he covered were concepts of chemical potential and free energy, or the available energy, which we're going to talk about. We'll talk about chemical potential in the next chapter. The Gibbsian ensemble ideal, statistical mechanics. If you take a upper level physical chemistry class, you'll do some of that. Gibbs phase rule. He was called the greatest thermodynamicist of all, who founded a new department of chemical science, which is becoming comparable in importance to that created by Lavoisier. Willard Gibbs is, in my opinion, one of the most original and important creative minds in the field of science America has produced. Albert Einstein. To physical chemistry, he gave form and content for 100 years. Wilhelm Oswald of the Oswald process. So it's a big kudos from big names. So, Gibbs free energy. If delta G is negative, the forward reaction is spontaneous. This is your criteria for spontaneity. Put a big smiley face next to it, give it a little star. That is my reaction spontaneous or no? Is really saying, is delta G negative? If delta G is 0, the reaction is at equilibrium. Both my forward and reverse processes are happening. If delta G is bigger than 0, if it's positive, the forward reaction is non-spontaneous, but the reverse reaction is spontaneous. So looking at our combinations of delta H and delta S, that will give us a delta G. If delta H is negative and delta S is positive, delta G is always going to be negative, so it's going to be spontaneous regardless of the temperature. Right? If delta H is positive and delta S is negative, then delta G will always be positive, meaning it's non-spontaneous at all temperatures. Then you got to look and see, well, is my delta H negative and my delta S negative? Well, delta G could be positive or negative depending on the temperature. It's going to be spontaneous at low temperatures, where the delta H term is going to win. Right? So if I go up to this HT A delta S, right, I want this temperature to be small, so this term here becomes small. If my delta H is going to be positive and my delta S is going to be positive, it's going to be spontaneous at high temperatures. So both positive means it's going to be spontaneous at high temperatures, where this guy is going to be the delta T delta S term is going to outweigh the delta H, and it's going to be non-spontaneous at low temperatures. And this is just the same thing, but with a slightly, I think, more organized presentation, right? And some examples of that. Okay. So one of the cool things we can do is we can set delta G equals 0, right? And that is our equilibrium condition. And did we just do an entire couple of chapters that really focused on equilibrium stuff? Indeed, we did. So you're going to rearrange this equation and solve for T, which is going to be useful to calculate the temperature of a phase change, or you could use it to calculate the temperature at which a reaction goes from spontaneous to not spontaneous.